Hello, I am Sadim, and today I will present our work, GSViz, Progressive Visualization of Geospatial Influences in Social Networks. This work was developed at UC Irvine. Analytics of geospatial relationships on social networks can be used in applications such as viral marketing, which is word of mouth information transfer between socially connected users. It can also be used in personalized location-based recommendations using social relationships or in applications of choosing evacuation hubs based on locations of the strongly connected social networks. For example, one study from public health is interested in analyzing tweets related to topics about COVID-19 vaccine. Say an analyst is interested in how people's perception is affected by a few factors such as geographic locations and social influences over time. Visualizing the result of the geosocial network related to the topic helps the analyst gain quick insights. Notice that as the data gets larger, querying the base table takes time. Moreover, transferring the result over the network, assuming the database and visualization interface are not on the same node, also takes a lot of time. Finally, rendering the visual result also requires delay, assuming the visual result size is large, consequently affecting the user experience. One typical way to address this delay is to use progressive computation to break a large query into smaller chunks to be delivered in multiple batches. Each batch contains a subnetwork or a portion of the result so that the system is more responsive. Typically, slicing the query is done in a middleware that sits between the database and the front end so that a user submits a single query and the result is retrieved in batches that contains a sub-result. Notice that we solved the problem of visualizing the results responsively. However, as we accumulate more subnetworks, it becomes difficult to make sense of the result due to the visual clutter. What is visual clutter? Visual clutter is defined in general as either having too many objects on the screen, or the objects are scattered, or there are too many edge crossings, which is a definition of visual clutter that is special to graph visualization. Having fewer data elements reduces the visual clutter, or keeping the number of elements the same, but grouping them also reduces the clutter. Finally, avoiding edge crossing in graph visualization gives better visual aesthetic. Vertex clustering and graph clustering works reduce the number of elements on the screen by clustering the points or vertices. Vertex clustering works cannot directly be applied in the setting because they care about the points independently and not the edges between them. Graph clustering works, on the other hand, they do care about the edges. However, they have the freedom to move the points all over the plane, and they don't have the restriction of geospatial networks. Edge bundling works do not reduce the number of objects on the screen, but they group the edges together in a bundle to increase the white space. These solutions also cannot be directly applied to solve our problem because they are not incremental. Finally, graph layout algorithms try to reduce the number of edge crossings. To address the challenges of progressively visualizing a network while reducing clutter, we developed GSViz, which stands for Geosocial Network Visualizer. It's a middleware solution that manages the entire lifecycle of answering a visualization query request. In this presentation, I will focus on discussing two main modules, namely vertex clustering and edge bundling. Let's consider a baseline vertex clustering algorithm. Consider the snapshot of these existing clusters. An edge between two clusters is said to be a super edge because it's an aggregation of the edges across the two clusters. Upon the arrival of a new edge from a new batch, we want to know which clusters each vertex should be merged into. The algorithm uses a predefined radius to perform a range search around the vertex. We know clusters A and C are in L's range. Similarly, B and D are in R's range. Following the algorithm's policy, a point is merged into its nearest cluster. That means that L is merged into A and R is merged into B, resulting in a new super edge. Notice, however, that we could have avoided creating a new super edge, which potentially increases visual clutter by exploiting the fact that there exists already a super edge between two of the candidate clusters, C and D. We introduce our progressive edge-aware vertex clustering, PEAK, which uses the existing information of the relations between the clusters to merge points L and R into C and D respectively. The solution is very simple and straightforward, but it introduces a computational challenge as we have to know all the adjacencies and connections between the candidate clusters. This can quickly become a performance bottleneck as we get more candidate clusters in later batches, up to 1,400 in some queries. To solve this computational overhead, we propose to consider the super edge between the clusters rather than dealing with the vertices individually, then cross-check the relation between the candidate clusters. The vertices of the super edge are the centers of the clusters. First, we divide the space into a grid where each cell size is a predefined pixel or a few pixels. Then when a new edge arrives, we calculate the number of cells that are in its radius. We can quickly use the combination of a pair of cell ID to identify if there exists any super edge in the pair of cell ID. Then we can merge in any super edge that is in the range radius, not necessarily the closest. Now I will talk about the second technique to reduce the visual clutter of geospatial graph, which is edge bundling. Let me discuss the steps of a baseline edge bundling algorithm called force-directed edge bundling, or FDEB for short. When a new edge from a batch arrives, we need to curve it. FDEB does that by first comparing the new edge with all the previous edges seen so far from all the batches. And then it groups the new edge with all those that it is compatible with. And compatibility is defined using 4 metrics. In this example, E is compared with E1 and it is compatible. It is also compared with E2 and it is compatible. Finally, it is not compatible with E3. Once we identify the group of compatible edges, in this example, E1 and E2 only, FDEB curves an edge towards its compatible edges. In order to curve the edge, it is modeled as a spline with a set of control points so that we can control the position of these control points to drag each point slightly towards the direction of all its compatible edges. In this example, the algorithm moves the control point from E towards E1 slightly, then towards E2 slightly, then the final result of the new location of the control point is the summation of those two directions. The new positions of the control points form the curve. While this technique nicely reduces the clutter, it is slow due to expensive 2 steps. The first is computing the compatibility with all previous edges from all batches and using all compatible edges to drag the forces. To solve this, we propose PB tree, which stands for Progressive Edge Bundling Tree. It is an indexing tree structure to drive the search in a way to avoid exploring all the edges to compute the compatibility. We also use one node only from the tree to compute the forces on the control points instead of using all compatible edges. I will first explain the structure of the tree, then I will explain how to use it. The leaf nodes are the raw edges in the graph. Each internal node has an edge and a weight. The edge is the weighted average of the edges in the nodes under it, and the weight is the number of edges under it. Now I will explain how we can use the tree to do the bundling. When a new edge arrives, we first create a new node containing the edge and a weight of 1. Then Starting from root, we use the compatibility score to explore the most compatible branch until we reach the furthest node. We insert the new edge under the node. Then we update the weights of all previous nodes along the path. Finally, we use this parent node edge, which is P in this case, and its weight to compute the forces on the control points. P is nothing but the weighted average of its children with weight 2. In this case, instead of using E1 and E2 to drag the forces, we use P's edge and weight only. This reduces the computation significantly. I will now show some numbers comparing GSViz techniques to baseline solutions. We use 3 data sets as shown in this table. The left figure shows the vertex clustering performance. The incremental edge-aware is much faster, and the pace at which the response delay increases is slower thanks to our modeling of edges compared to individual and independent vertices. The right figure shows the incremental edge bundling performance compared to non-incremental one. We can see that the incremental bundling is much faster. We evaluated GSViz visual quality by conducting a user study. We asked 29 participants to evaluate the visual result, and we measured 2 metrics, readability and faithfulness. In general, GSViz visual quality was comparable to the baseline, while its performance was much faster. eSummary presented GSViz, which is a middleware solution to progressively visualize a geosocial network. We also presented 2 of our techniques, the progressive edge-aware vertex clustering and the incremental edge bundling using a PB tree index-like structure. Thank you for listening.